Hello everyone, welcome to our webinar entitled The Dynamic Modeling of a Rockfill Dam with Drystone Pitching. It is part of my PhD. I did it in the third year of my PhD, which I finished recently. So it's about the dynamic modeling of one of those rockfill dams that I will talk about in the upcoming slides. So to start with, I will talk about a bit about the PhD project and about the structures that I'm studying. So first of all, the study structures are dams, rockfill dams. So their body is composed of a backfill made up of rockfill. Such rockfill is in such type of dams is protected by a layer of hand-placed dry stones, which is called pitching in our study, which we can see here in green. And between this pitching and the dam body, so the rockfill, there is a transitional layer of denser rockfill, which we can see here in lighter blue. So we can see that it is a rearranged denser rockfill sublayer, which is used to facilitate the layage of the pitching above it. In addition, such dams are characterized by a berm, especially on the downstream sides, which has a width of 1 to 2 meters in such type of dams. And on the upstream side, we normally have a concrete mask, which is used to form an impermeable layer to prevent the leakage of water and fill the reservoir. Finally, such type of dams is characterized by a very steep slope of about 1/1, and which can reach values up to 1/2 on the upstream side. It should be noted also that such type of dams was built in the 1950s, and it's a bit an old design. So such type of dams are found in France. So we have about 10 of such dams, which are operated by EDF, which, by the way, financed my PhD project. The problem is that such dams, the mechanical behavior of them and their resistance are not very well studied and known. So, which is the problem that I'm trying to solve, that I try to solve in my PhD project. In the below figures, I'm showing on the left-hand side at the beginning, I'm showing the construction phase of a real dam. So we can see the damped rockfill in the middle and the drystone pitching, which is laid on the two phases of the dam. On the right-hand side, we can see a section of this same dam. We can see the rockfill in the middle and the drystone pitching on the two sides, which with a transitional layer of rockfill below it. So the main objectives of this study, this part of our study, is first to introduce a new mixed FDM-DEM approach, which is a continuum discrete element method approach, coupled approach for the modeling of such rockfill dams with drystone pitching. And by the way, this part of the study was presented in a previous webinar last year. For this webinar, the main objective is to build a dynamic model which is able to retrieve the truly dynamic and seismic response of such dams. And finally is to evaluate and quantify the dynamic resistance of such dams. To start with the validation of this approach, I will do some, I will repeat some of the slides that I presented in the last webinar. So first of all, to validate this approach, we needed an experimental data. So what we had is we had an experimental campaign which was done on 1/10 scaled down physical models. So such physical models of rockfill dams with drystone pitching were built inside of a bucket, as we can see here in the down right figure. So they were built inside this bucket with a height of about 2 meters and a slope of 45 degrees. The loading of this dam was provided by the rotation of the bucket. So one side of the bucket was lifted by a crane track, and it was rotated gradually until reaching failure, as we can see here in this diagram. So to validate our approach, we modeled this experiment. So the dam body, which is made of rockfill, was modeled as a continuum medium using Moore-Coulomb and Alka and Roche constitutive models. So we did two cases. It was modeled on FLAC3D. And by the way, Alka and Roche, which is denoted Alka E in our study, is an elastoplastic model developed by EDF especially for the modeling of rockfills. For the drystone pitching on the two phases of the dam, they were modeled discretely on PFC3D. And then after generating the dam body on FLAC3D and the drystone pitching on PFC3D, we have coupling between the two softwares. I'm showing you here a summary of the comparison between the numerical and experimental results, which validated our approach. So first of all, on the left-hand side, we have the numerical failure angle as a function of the experimental failure angle for 4 different cases which were studied. The difference between the 4 cases is just in the material of the drystone pitching and their dimensions. So we can see that the numerical model using either Moore-Coulomb or Alkan-Roche model, they were both able to retrieve the experimental failure angle with a very precise way. The difference between the two models can be seen when we compare the displacements. So when we go to the right figure, we have here an example of the displacements of some of the points on the downstream pitching of our experiments. This is just one case, which is case 4. So for the upper part of the dam, we have here, and middle part of the dam, middle part of the drystone pitching, the downstream part. So the experiments are the blue crosses. The numerical one using Alkan-Roche is the yellow one, and the numerical one using Moore-Coulomb is the gray one. We can see that Alkan-Roche was able to give very accurate gradual increase of displacements as a function of the rotation angle, whereas Moore-Coulomb underestimated this displacement, which was expected due to its stiff behavior. So far, as a final conclusion of the study is that the numerical approach was validated using the Alkan-Roche model. Now, starting with the real scale dam, which is the dynamic modeling of it, I'm showing you here the historical section of this dam that we are studying. So it's a 16 meters height dam. It's formed of a damped rockfill and protected by a stone pitching with a rearranged hand-placed rockfill layer between them. This dam lies on a moraine layer, which by itself lies on a rocky massif. And on the upstream side, we have alluvium. And on the upstream toe of the dam, we have a concrete barrier. So the numerical model that we built for such dam is presented here. We have here the rockfill, the pitching in green, which we can see a bit, and the transitional layer in dark blue. And this model is a 3D model. It's not a 2D model. It's a slice of the dam. So we have a thickness in the y direction. I will talk first about the boundary conditions that we used in our dynamic simulation. So first of all, for the signal that was applied, it was applied at the base of the foundation, as we can see here. And at the same base, we applied an absorbing a quiet condition in order to absorb all the waves and to prevent any reflection of the waves. On the two lateral sides of the foundation, we have a free field boundary to simulate a semi-infinite medium of the foundation to prevent any reflection of the waves also. And for the different parts of the foundation of the dam, we have here the shear wave velocity. For the rock, it's about 3,000 meters per second, which is expected due to its rigid characteristic. For the moraine, it's about 400 meters per second. And at the base of the dam, it's about 340 meters per second. And for the dam, it changes as a function of the pressure. So this value is just at the base. For that signal that was applied at the base of the foundation, so two artificial conservative signals were used. The first signal, we can see it here, it's characterized by a 0.16 G PGA, a dominant frequency from 5 to 7 Hz, and a strong phase duration of about 10 seconds. This signal was applied in the horizontal direction, which is the X direction in our model. Another signal that was used is shown here in the bottom. It is used to apply it in the vertical direction, so which is the Z direction in our case. This signal is originally a horizontal signal. So what we did is that we took 2/3 of it to be applied in the vertical direction. So we took a ratio of about 2/3 between the vertical PGA and the horizontal PGA. For the constitutive model and parameters that we used in our dynamic simulation. So here for the dam body, we used a hysteretic model in the dam body and in the foundation. And in addition, it was coupled with more Coulomb to limit the elastic domain by a failure surface. The parameters and curves, most of the parameters and curves were deduced from the literature. And some of the parameters of the hysteretic model were calibrated by fitting the degradation curve that we can see here. Here we have G over G max, the shear modulus, maximum shear modulus, as a function of the cyclic deformation, and here we have the damping as a function of the cyclic deformation. So we have some data from the literature. We try to calibrate our numerical parameters by fitting these two curves. And for the maximum shear modulus of each zone in the dam body, it was defined as a function of the pressure developed in each zone. Here I'm showing you some of the results. So we have two videos here. On the left-hand side, we have the horizontal displacements as a function of the 20 seconds earthquake that we are modeling, and on the right-hand side, we have the vertical displacements as a function of the time. So at the end of the shaking, we have a crest settlement of about 14 centimeters and a crest horizontal displacement toward the downstream side of about 16 centimeters. At the end of the earthquake, I'm showing here also the deformation state of the dam. So we have shear strains up to 12% that are developing here on the downstream side of the dam, parallel to the downstream pitching. Now, so if we want to justify our results to see if it's giving some reliable results or not, we try to compare it with some of the historical statistical crest settlements of the dams during an earthquake. So we have this table from the literature. It's giving the crest settlement of the dams of similar dams as a function of the peak ground acceleration PGA. Here, the crest settlement is calculated as the following. It's equal to the crest settlement divided by the dam height, in addition to the height of the deformable layers under it. So if we place the point that we got in our numerical model, it's at 0.16 G, the PGA. It's on the upper bound of the statistical data. This may be due to the conservative signal that we used in our study, which would give us the most conservative results. So what we tried to do is we tried to get some real signals, real recorded signals, which we took from a lab. These signals are recorded in the region where the dam is located, and they are less conservative on the side of the spectrum, and they have lesser strong phase duration. So if we trace them, we tried several recorded signals. We have less displacement than the initial numerical model, which was expected since it's less conservative. And with those recorded signals, we have better results and close to the statistical data. Now for the dynamic safety factor calculation. So here it's used to quantify the dynamic resistance of this studied dam. We have two approaches that we used. The first approach is the PGA augmentation. This approach is based on the fact that the applied signal is scaled up gradually. So we increase the PGA gradually. It's multiplied by a scaling factor. Here the scaling factor is equal to the PGA at the final scaling factor is equal to the PGA at failure divided by the initial PGA, which is equal to 0.16 G in our case. What we have seen is that the dam is stable at a scaling factor equal to 3, and it failed as a scaling factor equal to 3.3, concluding that the dam can withstand a PGA up to 0.48 G from our study. I'm showing you here the failure mechanism that we got at a scaling factor of 3.3. We have the displacement magnitude of the dam and the pitching at 12 and 13 seconds of the earthquake. We can see that the whole downstream part is sliding, and we can see that the end of the failure is at the bottom downstream part. We can see that downstream pitching is starting to dismantle. The second approach that we used is the reduction of the resistance parameters. So what we did here is that we degraded the parameters of the dam before doing any dynamic simulation, and then we got a static equilibrium using these degraded parameters, and then using this degraded static state, we did the dynamic computation. We applied the signal to it. Here, the safety factor is defined as the smallest degradation factor inducing dynamic failure. For our case, after our study, the dam was stable at a degradation factor equal to 1.25, and it failed at a degradation factor of 1.3. I'm showing you here also the failure mechanism at a degradation factor of 1.3. The same mechanism as before is seen, so sliding at the downstream part and dismantling of the bottom part of the pitching. So the conclusion of this approach is that the safety factor is dynamic safety factor defined here is between 1.25 and 1.3. So that was it for some of the conclusions in our presentation. So for the mixed FDM-DEM approach, it was validated by modeling scale-down experiments on the resistance and deformation side. For the dynamic study on the real scale dam, we have crest settlements which are close to the historical statistics of such type of dams, which comfort our choice of parameters. We have seen that the dam is able to resist PGAs up to 0.48 G using our signal, and we have seen a dynamic safety factor of 1.3. Thank you.